in the last class we had talked about the essential method of solving differential equations, and we said that even if we forget the exact method, we cannot exactly solve the equation fine, but nevertheless the qualitative character of the orbit in the state space, that should be understood. And for that, the route that we had taken was that in the whole state space, which would be normally nonlinear, we identified the points that are equilibrium points. These are given by x dot equal to 0, where x is the state vector. Solving the right hand side, we had obtained that, and from there we said that fine, we have now identified that this is the equilibrium point, and we will look at only the local neighborhood of that, and in that neighborhood we can locally linearize it. So, we used the Jacobian to linearize that. So, here the Jacobian would be representing the local linear behavior. So, we obtained a linear set of differential equations. And then if we concentrate on that neighborhood, the essential method of solving the equation would be to identify the eigenvalues and eigenvectors. We had also said that since the eigenvalues are obtained by an equation of this form, do you remember that? A times x is lambda x, which yielded a minus lambda I times x equal to 0. So, this its determinant had to be 0, and that yielded the eigenvalues. Now, in that I said that the eigenvalues then would be the result of a quadratic equation in a 2-dimensional system, a cubic equation in a 3-dimensional system, a 4th order equation in a 4-dimensional system, and so on and so forth. And if we take the simplest case, the quadratic equation that has various possible types of eigenvalues, the eigenvalues could be negative, positive, real, complex, all these possibilities exist. So, in each case we wanted to understand the qualitative character of the orbit. The exact solution, I said that you study from the differential equation textbooks. I assume that you have already come knowing that. If you have forgotten that, just read any differential equation textbooks. I am not going into that, but for our purpose it will be necessary to understand the qualitative character of the orbit in the state space. And in doing that, we had come to two cases. One, if the eigenvalues are real and negative, if the eigenvalues are real and positive, and eigenvalues are real, one positive, one negative. These are the three cases we tackled. Just to briefly recapitulate what we said, that in the state space there will be certain directions, the eigen directions, and if you take a vector along that direction, then your x dot is equal to f x, that was the equation that we started from. So, this would be a linear equation in the right hand side. Then your, if this is the eigen direction, then x dot will be in the same direction, and this vector will be this vector, that means x vector times the eigenvalue will be the x dot vector. So, if the eigenvalue is positive, then the x dot vector will point in the same direction as the x vector, as a result of which the x will keep on increasing in this direction and go out. That represents an unstable system. If it is a negative eigenvalue, then the x dot vector will point in the opposite direction, and therefore, the distance from the origin will exponentially reduce, and ultimately it will converge onto the equilibrium point. That is what we said. Following that argument, we concluded that if there are two eigen directions in the system, then if the eigenvalues are negative, say -1 and -3 in both the directions, then the behavior would be like so. Thus, we drew what is known as the vector field. The character of the vector field will be like so. Okay. If we have the eigenvalues positive, that means +1 and +3, it will be just the opposite, arrow direction will be opposite, but the character will be the same, it will be unstable equilibrium point. And then we went on to consider the case where the eigenvalues are one positive, another negative. That means, again let us draw. Suppose this is one eigendirection and this is another eigendirection, and suppose here it is -1, here is +3. Then the behavior would be, again starting from any initial condition, the essential point is that you are decomposing this vector into two directions, into the components along the eigen directions. So, here is one component, here is another component, and this component will reduce, this component will reduce, and this component will increase. So, this fellow will go like this. Similarly, any initial condition here will go like that, any initial condition here will go like that, any initial condition here will go like that, and that is the character of the vector field here. And we said that that goes by the name of a saddle. So, we start from there. Okay. Remember, these saddle points are very important for our future discussions. So, the saddle equilibrium points will have to be understood quite well. Apart from these, what other behaviors can there be? What other types of eigenvalues can there be? Complex. Well, if you draw the complex plane, real and imaginary, then we had considered this plane, this line real negative, we had considered this line real positive, and now suppose there are two eigenvalues here and here. Of course, you know that eigenvalues, if they are complex, they also always have to be complex conjugate, they cannot be just one here another here, they always have to be complex conjugate. If they are here, then what will be the character? Again, we will consider the two components, two parts. This is the real part and this is the imaginary part. Real part will cause a e to the power lambda t type of behavior. So, if this lambda, real part of the lambda is negative, then it will be a e to the power minus something t, it will result in a decay. Decay of what? Decay of whatever is the result of the imaginary part. Now, imaginary part will result in e to the power j omega t kind of behavior, which is nothing but a sinusoidal behavior. So, we conclude that if it is purely imaginary, then you have a pure sinusoidal behavior. If it is imaginary with a negative real part, then it will be a sinusoid, but damped sinusoid, it will decay. And if it is a complex with positive real part, it will be like this. This will be a exponential envelope. Clear? This is all we need to know really, as far as the linear neighborhood is concerned. As far as the linear neighborhood is concerned, this is all the information that we really need. By the way, the frequency of this oscillation depends on what? The imaginary part, yes. So, the undamped component depends on the imaginary part, damped component will be slightly changed. Fine, depending on this, can we now work out a problem? Let us see. Suppose there is a system whose differential equations are x double dot plus x minus x cube is equal to 0. Okay. How will its behavior be? I want to deduce that by looking at the local neighborhoods of the equilibrium points, right. So, in order to approach this problem, how will I deduce the equilibrium point? Remember, the first step is to obtain first order differential equations after this. So, first order differential equation, in order to obtain it, just say x dot is equal to y, and then y dot is equal to, bring this to the left hand side, y dot is this. So, minus x plus x cube. Okay. So, this is the set of equation, differential equations. Now, we need to obtain the equilibrium points. Equilibrium points are where this x dot is set to 0, y dot is set to 0. X dot set to 0 gives y is equal to 0, and y dot set to 0 gives so it gives x cube minus x is equal to 0. There are 3 solutions, right? What are they? So, the equilibrium points then one is 0 minus 1 1, is it? So, minus 1 0 0 0 and these are the 3 equilibrium points, right. The next step would be to try to understand what is the character of the vector field in the neighborhood of each of these equilibrium points. Okay. Can we deduce that? Quite easily. So, now let me draw. Here is the whole of the state space, here is the point 0 0, here is the point minus 1 0, and here is the point plus 1 0. Okay. The next step is to look at the local neighborhood of this point, and this point. How will you do that? We will say that now we are considering the deviation from the equilibrium point. So, deviation of delta x dot and delta y dot, these will be given as, here is the Jacobian matrix delta x delta y. The Jacobian matrix is okay. So, here is your F1 and here is your F2. So, what is this particular component? 0, this component 1, this component 3x square minus 1, and this component good. Now, we need to evaluate this not just anywhere, but at the 3 equilibrium points. So, these 3 equilibrium points are minus 1 0, 0 0, plus 1 0. Yeah, because F1 is just y. No, y is not the opposite way. Here it is x dot, in the right hand side just you are asking what function of x and y, and that function is not a function of x, it happens to be just a function of y. So, if this is the F1, okay, in general you would write that x dot is equal to F1 of xy and y dot is another function of xy. Okay. So, this one is answering the question how does x change with time, x dot, and that is given by the specific position in the state space x and y. Now, it so happens for this particular system that x dot does not depend on x, but depends on y. So, it comes as 0. So, at these three locations, we will need to substitute -1, 0 and 1 in place of the x values to obtain three different Jacobian matrices at these three locations. Obtain that. So, for this particular location you have 0, 1, 0 and 2. At this location what do you have? 0, 1, -1, 0, and at this location you have 0, 1, same, because it is squared. Okay. Now, the next step is to obtain the eigenvalues and eigenvectors. Obtain that. Let us start with this particular point where the location is -1, 0. This is the eigenvalue. This is the Jacobian matrix. What do you get as the eigenvalues? Come on, it's simple. Plus minus 1. Huh? No. This one cannot be that. Right? Yes. Plus minus root 2 you will get. So, here the eigenvalues are plus minus root 2. Plus minus root 2 means what kind of equilibrium point is it? A saddle. A saddle means then I have to identify the eigen directions and then I can now put arrows. Okay. Can you find out the eigen direction? That means which is the eigenvector in associated with the eigenvalue plus root 2 and which is the eigenvector associated with the minus root 2 eigenvalue. I hope you remember how to calculate eigenvectors and eigenvalues. Is there anybody who cannot? So, in general I will draw them as this, but you have to calculate and tell me what are the slopes. Y is equal to root 2x, is that right? Which one? No, plus root 2. Yeah, the eigenvector associated with the plus root 2 eigenvalue is y is equal to root 2x. That is what you said. Now, y is equal to root 2x plus root 2 eigenvalue means it is the outgoing direction. Y is equal to root 2x means it is in this quadrant. So, I will say these arrows and the other eigenvector is y is equal to minus Are you all getting that? If somebody has any difficulty, please ask. I will then explicitly calculate. Huh? So, not 1 by root 2, minus root 2x. Yes. Okay. Minus root 2x. Y is equal to minus root 2x means what is the direction? What is the angle? Y is minus something x, so it is this vector. and then it is associated with minus root 2 eigenvalue. So, these are the incoming eigenvectors. Fine. What will happen here? Since the Jacobian matrix is the same, so it is not necessary to calculate it all over again. We can safely draw the directions and put the similar arrows. Right. Now, let us come to the middle one. Let us come to the middle one. What is the eigenvalue? What are the eigenvalues of this? So, these are purely imaginary eigenvalues, plus minus j. There is no fun in calculating the eigenvectors, because they will not be real eigenvectors. Eigenvectors will also come to be complex conjugate eigenvectors. They will be useful in obtaining the actual solution. So, if you want to obtain the actual solution in writing, you need that, all right. But here today we are not concentrating on that, we are concentrating on developing an idea what the orbit looks like, and for that it will suffice for us to know that if the eigenvalues are purely imaginary, there is no contraction, there is no dissipation, the sinusoid will not die down, and so in this state space how will it look? Circles. Okay. So, they will look circles. Suppose you start from this initial condition, you will get a circle. Suppose I start from this initial condition, you will get another circle, so on and so forth. Okay. But you cannot really carry on this argument ad infinitum, because this argument holds in the close neighborhood of this one. It will be circle only in the close neighborhood. As you go far and far, it will no longer remain circles. Okay. But then I will ask you, with this much information obtained out of looking at the local linear neighborhoods, can we infer what will be the character of the vector field in the rest of this state space? This much we have been able to obtain simply by calculating the eigenvalues and eigenvectors. Can we infer? Well, on that there are two ideas about vector fields which will be useful. One, vector fields behave something like magnetic lines of force, in the sense that they do not ever intersect. Magnetic lines of force, do they intersect? They do at the poles, but elsewhere they do not, right? Elsewhere they do not. You cannot have a magnetic line of force intersecting. You cannot have the vector fields also intersecting. What would it mean? Suppose at this point, if there are two vector field lines intersecting, then if the initial condition is here, it will not know where to go. Okay. The moment you have defined the differential equations, at every point there is a unique vector, means they cannot intersect. All right. There is another idea, that is, unless there is some very strong reason to believe so, the vector fields will be smooth. That means they will not suddenly twist and turn everywhere. Which means that, why did I say that? Let us see the application. We have seen that here these will be rotational, this will be rotational. Can you tell me whether it will be clockwise or anti-clockwise? How do you know? The equations do not say that. No, the equations do not say that. The eigenvalues do not say that. The eigenvectors do not say that. Right? Eigenvalues do not say whether it is clockwise or anti-clockwise. They only say that it is rotational. You can have perfectly sinusoid with both clockwise rotation as well as counterclockwise rotation. So, what will be the direction of rotation? Okay, if you say clockwise, justify. Why clockwise? Because as you go far and far, it should smoothly go into this one, and here you can see a movement like this. and that gives a rotation. There is another way to infer whether it is clockwise or anti-clockwise. Just choose a point somewhere here. This is a point with x coordinate existing and y coordinate 0. Put it into the original set of equations. X coordinate positive, y coordinate 0. You can now obtain what is the vector. Say x coordinate is 0.1 and y coordinate 0. X dot is 0 and x coordinate is 0.1. You can calculate this. You will get this as a negative number because of this, right, which means that here the vector will be pointing like this. Once you do that, you do not really have to do this exercise for every point because of that theorem that they do not turn and twist, they more or less smoothly change. So, you cannot have just one vector here pointing this way, another vector here pointing that way. No, it is not possible. So, combining these two ideas, it is now possible to sort of intuitively construct what can be the behavior of the system in this part. For example, here it is bound to be like this. Now, you can see that there is one eigenvector direction going. Where will it go? It will come back onto this, and this one will come back onto that. In between, you will have one type of behavior. In the center, towards the center, it will be more or less perfectly circular, which means the time domain behavior will be almost perfectly sinusoid. As the oscillation increases, the amplitude of oscillation increases, it will be distorted sinusoid. Can you see that? Has to be. Now, as you go further and further, if you cross this point, it will be like this, it will go to infinity. Starting from any initial condition here, it will go to infinity. Starting from any initial condition here, it will again, there is no other way. Can you see that? Starting from here, there is no other way, it has to go like this, and there is no way that it can enter this whirlpool, right. So, see, starting from only the view of the local linear neighborhoods, without really solving any equation, it was possible to infer things of interest about the overall character of the vector field, right. What ideas did we really make use of? We really made use of the idea that we can identify the behavior in these local linear neighborhoods by simply obtaining the Jacobian matrix and its eigenvalues and eigenvectors. We will then draw the local vector field and then extend it with those two ideas that they cannot sharply turn, that means their changes have to be smooth changes, and two vector field lines cannot cross, except the way you had the magnetic field lines crossing at the poles, they can also cross at the equilibria, at the equilibrium points, where actually the magnitude of the vectors is 0. Okay. At those points they may intersect. So, you see, in the whole of the control theory, you take a look only at these points. You know that here there is a system whose equilibrium point is like this, its behavior is like this. If you have a small perturbation, it will be a sinusoidally. We know that, and that is what the whole control theory will be based on. And in that small neighborhood, you can apply all the techniques that you have learnt in control theory, Laplace transform, root locus and stuff like that. Go out, that doesn't apply. And by looking at the local linear neighborhood, you have no idea that there are actually very, very different kinds of dynamics possible in the system. What different kinds? For example, starting within this island, it will always be oscillatory behavior. Anywhere outside this island, it will collapse, it will go to infinity, right. Start from here, it will go and run to infinity. That means the system will become unstable. That means that here the system can have a stable oscillatory behavior only within a certain range, okay, only within a certain domain, and these lines separate two different types of behavior of the system. Same system may collapse, same system may nicely work like an oscillator. Can you see that? It can nicely work like an oscillator here, and if there is some way, there is some excursion due to noise, due to perturbations, due to somebody hitting with a hammer, whatever goes there, the system will collapse. The overall picture of the vector fields tells you that. Okay. So, are you now comfortable with the idea of vector field? So, the idea is that if you look at the vector field, you can have a clear idea what can happen to the system, and often for that it is not necessary to actually solve the differential equations. In general, you will be able to solve the differential equations only in these closed neighborhoods. Elsewhere you will not be able to solve, because they are nonlinear differential equations. They will be solvable only by numerical means. Fine. With this amount of ideas, let us simply work out. I am giving you the task of working out now. The simple pendulum. Simple pendulum. Here is a support. From here, this fellow. Obtain first its dynamical equation. In terms of theta, of course, you will not do it in x, y, z coordinate, that will be foolish. You will do it in terms of theta. You can do that. Here is a length L, here is a mass m. Okay. How will you proceed? Also assume a bit of friction, air friction. That will make it deviate slightly from what you did in school, right? Can you write down the differential equations? Have you learned how to? Okay, if there is no air friction, it will be theta double dot is equal to minus no I will assume that you know. This was done in school, come on, why are you looking so blank? This was done in school. The only problem that you did in school was that sin theta was approximated by theta, and then you went ahead. Okay, let us assume, since you look a little bit blank, so let us forget about the friction part. Let us start with this. Theta double dot is minus g by L sin theta. Now, let us make your life even simpler. You can always have a pendulum 9.81 meters of length, right? If you have a pendulum 9.81 meters in length, what will happen? This will be unity. So, for G is equal to L, you have theta double dot is equal to minus sin theta. Of course, we will need to write these in terms of first order differential equations. So, we will say let theta is equal to x and theta dot is equal to y. Then the equations are x dot is equal to y and y dot is equal to I do not want you to put sin is equal to x as yet. Okay. Now, what are the equilibrium points? Yeah, there will be an infinite number of equilibrium points. Y is equal to 0, of course, but sin x will assume 0 value for 0, pi, 2 pi, 4 pi, so on and so forth. So, there will be infinite number of equilibrium points, but let us draw a few of them. This is 0, this is say 2 pi, or let us say pi, and here it is minus pi. Okay. Imagine the pendulum, 0 is hanging downwards, right, to pi is up, minus pi is in the opposite direction goes and goes up. So, that is minus pi. So, plus pi and minus pi are really the same, and 0 and pi 2 pi twice pi is also the same. 0 and minus twice pi also, it is essentially the same thing carried over and over, but mathematically it yields a infinite number of equilibria. But for our purpose, it will suffice to keep ourselves within this range. What are these equilibrium points? For example, what is this equilibrium point? You will have to then locally linearize it, obtain the eigenvalues and eigenvectors, and then only tell. You cannot really just say like this, no. You have to say after having calculated that. So, what is this equilibrium point? When I say what is this equilibrium point, I guess I am expecting names, right? And while doing this exposition, I have given only one name, so I need to give more names. If both the equilibria are, both the eigenvalues are negative, then you know that all vector fields converge. Then that is more or less like a sink, right? A sink in your bathtub, if you open the sink, every water goes in, right? So, it is a sink, simple language. If eigenvalues are both positive, then it is a source. Okay. So, two names, if the eigenvalues, both eigenvalues are negative, it is a sink. If both eigenvalues are positive, it is a source. If one eigenvalue is positive, another negative, it is saddle. And if you have complex conjugate with negative eigenvalues, negative real part, in the state space the behavior will be what type? Will be in the time domain, it will be like this. In the state space, it will be spiral, incoming spiral. Okay. It will be a spiral sink. Similarly, this type, where the eigenvalues are having real positive real parts, it will be spiral source. Okay. So, these are the names. Based on these names, call them. What are they? Huh? This fellow, what is it? Is it a source, sink? Is it a saddle? I want concurrence. It will be trivial to calculate that. In this equation, you will have to take Jacobian, right? Jacobian means minus sin x, it will be minus cos x, and then x at 0, you will have to evaluate and put it. You get what here? Plus minus 1. Plus minus 1 is a saddle. So, it will have 45-degree lines as the eigenvectors, again almost the same kind of behavior as we just showed. And here no, not spiral, no, not saddle, it will be circle behavior, yes, it will be circle kind of behavior, the way we just did. But now we can easily put the arrows here, because we know that it has to go like this. Okay. So, again for the pendulum, the behavior would be something like this. The reason I did this is, notice that its behavior is more or less the same as the one that we just evaluated, more or less the same. Only thing is that this pattern is repeated ad infinitum. That means this fellow goes, and here there will be again a circular behavior. Again, sometime here there will be another circular behavior, so on and so forth. It will go on in the state space. But now, can you relate this with the physical behavior of the pendulum? Physical behavior of the pendulum. This rotation, this oscillation. Okay. Normally, you just move it and oscillate it. It will oscillate like this. Where do you see it on the vector field? Which orbit? It is this orbit. Okay. Around 0, 0, it goes on oscillating. So, a oscillatory orbit in visually, what is oscillatory will be seen as a closed loop in the vector field. In the state space, it is just a closed loop. Fine. So, after some time, it becomes sort of a distorted closed loop. Fine, but nevertheless a closed loop. What happens if you start here, or what happens if you start slightly up? You notice that there is a speciality here. If you are exactly here, you don't know where to go, but if you are slightly away from it in this direction, it still go on rotating, right? You can see that from the vector field. If you are slightly off this way, then it will have to go like this. It cannot ever do anything else, right? Physically, what is happening here? Now, what are these? Here is your theta direction and here is a theta dot direction. This is minus pi up there. Theta direction means slightly off and at 0 velocity, right? If you start, what will happen? It will go like this and go like that. It will still be oscillatory behavior, okay? But if you are here, but give a velocity push, it will go on rotating, and the rotational velocity, rotational motion will translate into the state space as not a rotational motion, remember, as a motion like this. Okay. So, are you getting a feel for the nonlinear behavior of such a simple system? Too simple really, but still nonlinear. In school you had only taken a close look at this point where you approximated sin x by x, essentially that is local linearization. So, by locally linearizing you have taken a look at that, but the overall behavior of the simple pendulum is not that simple, and that becomes clear only when you take the sin x into account and work out the whole behavior of the state space. Okay. Fine. We do not have much time left, so let us talk about something else. This might give you the impression that this method that I was talking about, the method was identify the equilibrium points, work out the behavior around the equilibrium points, and then join the vector field and go by sort of common sense way. That will suffice in understanding any nonlinear dynamical system. It will give that kind of impression. Well, for the next 5 minutes I have to dispel that myth. You cannot really do that. That works only in some rather simple systems. In the main run of nonlinear systems, you cannot deduce the nonlinear behavior by looking at the linear behaviors. What we are doing? We are looking at the linear behaviors piecemeal. Here is a linear behavior, here there is a linear behavior, here there is a linear behavior, join them, you get the whole. No, the whole is not always just a summation of the parts. More things can happen. When? Well, in order to understand that, let us look at the situation. I will write down the equation there, then it will be easier for you to understand that. Okay, suppose there is a system whose vector field is like this. What will you say about the equilibrium point? What is its name? Incoming spiral behavior. The equilibrium point will be called a spiral sink. Okay. Suppose there is a system with a spiral sink type of behavior. Now, any system has some parameters. For example, an electrical circuit has parameters like the inductance value, the capacitance value, the voltage applied, the resistance. If you have a rheostat, you are changing, it means you are changing a parameter. Similarly, you have the pendulum, in which the length of the cord is a parameter. Air friction is a parameter. By the way, if you add air friction, what will happen to this fellow? Yes, all these things no longer remain, they will become incoming spirals. Okay. Else they will no, else also there will be a problem. Try to construct it by drawing incoming spiral in these places. You will notice that you can no longer bring this to here. It will come in inwards. Okay. So, before we go on to the other things, let us just illustrate how will it look. If you have a pendulum with friction, suppose these are the 3 equilibrium points, and here I know that the behavior is like so, and here I know the behavior is a saddle with eigenvectors going like this, eigenvectors going like that, and therefore this one will go like this, it will not go there, but from here it will. So that if you start from that kind of a position, which I said up, but with a push in velocity, then also it will not simply go on rotating, but after some time it will enter, and that is it. Okay. So, this becomes clear the moment you try to by hand construct it, you understand that that is going to happen. For the pendulum, physically the system is simple, but for more complicated system this gives a lot of insight, this kind of approach of drawing the vector field. And in general it is possible to draw the vector fields for a two-dimensional system. If you are using Mathematica, Maple or MATLAB, all these programs allow you to draw the vector fields. There are commands by which if you give the system of equations, it will draw the vector field for you. But that vector field will not look like this. That vector field will look like, here there is a point, an arrow, 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 again here there is a point, there is an arrow, here there is a point, there is an arrow, and a field of arrows it will draw. But from there it is more or less clear how the behavior is. It will be instructive therefore for you to learn those commands in MATLAB or Maple or Mathematica, whichever program you are comfortable with. For this course you will have to write programs in one of these high-end softwares, programming languages, but I will not command which one you will use, and you can use anything that you are comfortable with. Some people may be comfortable with Scilab, SCILAB, probably you know there is a free software available. Some people may be comfortable with MATLAB, some people may be comfortable with Maple, Mathematica, whatever. All of them have the facility. Okay, now where were we? We were talking about the situation where you have a incoming spiral orbit. If you have an incoming spiral orbit, let's take a system where it will happen really. X double dot minus mu 1 minus x square x dot plus x is equal to 0. Can you calculate the behavior of the system? With the tools that you have learned, you should be able to. What will you do? First we will decompose it into second order system. So, we will say x dot is equal to y and y dot is equal to mu 1 minus x square into y minus x, right. We said x double dot is y dot, this the rest of it taken to the right hand side is just this, clear. Where are the equilibrium points? 0 0, x dot 0 means y 0, and then y 0 means this whole thing is 0, therefore x is 0. So, 0 0, here is the 0 0. Now, can you find out the Jacobian? Now, notice the mu is a parameter. The way I said, your voltage is a parameter in a system, the length of the cord is a parameter in the system, the friction of the wind is a parameter of the system. At the bottom of the pendulum, if you have a magnet, that will change the parameter of the system, so on and so forth, it will change the gravity. So, mu is such a parameter. Nevertheless, it appears in the equation, and therefore, you should be able to obtain the local linear behavior including this mu as a function of this mu. Okay, do it. You will get from if you take the deviation from here, x dot y dot in the local linear form will be 0 1 no, the Jacobian will contain other things, and then if you put 0 0, then only you get those things out. Okay, so first write the full minus twice mu x y minus 1, and here it is mu minus mu x square, right. Okay. Now, if you put this takes the form 0 1 minus 1 Now, the rest you take as an exercise that we will do before coming to the next class. For mu values negative and for mu values positive, you calculate the eigenvalues. Therefore, as you change mu as a parameter, the vector field will change this way, right. So, in order to try to understand how the vector field changes as you change a parameter, you simply imagine that you are changing mu across from a negative value to a positive value, and tell us in the next class what will be the behavior of the system as that happens. Okay. And then that will be the starting point of another derivation. Okay, that is all for today.